third talk will be Semantic-Type-Guided Bug Finding, and will be presented by Kay Wu.
Can you hear me? Nice. Okay, good afternoon, everyone. Thank you all for coming to this talk. My name is Wu Ke, and I'm a member of the PL lab at Johns Hopkins, led by Dr. Scott Smith. I'm excited to talk to you about our lab's work, Semantic-Type-Guided Bug Finding. Anyone here is a fan of static type checking? I really hope you are, because otherwise you probably came to the wrong talk. So let's talk a bit about static type checking. A common theme is that they almost inevitably rely on type systems. Unfortunately, it is impossible for a type system to be sound, complete, and decidable at the same time, so a trade-off must be made. Many practical type systems today are sound and decidable, but sacrificing completeness leads to good programs being rejected, limiting the language's expressiveness. So naturally, as researchers, we started wondering, can we do something else instead? More specifically, can we make a type checker without relying on traditional type systems? And building upon that foundation, can we also make the checker both sound and complete? That is to say, can we find all real type errors in a program and only those errors? So let's start with replacing type systems. Type systems are essentially a syntax-directed approach to typing. And if we want to do away with it, the natural alternative is a semantic-directed approach, which is aptly named semantic typing. And as its name suggests, semantic typing is where types are determined solely by the behaviors of an expression rather than any syntactic structure. In contrast to type systems, which use logical system as their foundation, semantic types use a semantic model to define the meaning of types. For example, in semantic typing, the type int includes any expression that evaluates to an integer. So to illustrate the difference, let's look at an example. In many type systems, a conditional is required to have the same type for both branches, and thus an expression like if true, then 0, else false would fail to type check in such a type system, but it will type check if we use the semantic definition of int. So this is a simple case, but it demonstrates how semantic typing has an edge over syntactic typing in terms of expressiveness. But there is a reason why semantic typing isn't widely used in type checking. Essentially, semantic typing is asked to run the code to a degree in order to perform type checking, which means if we want to use it statically, we must find a way to determine program behavior at compile time. But in general, the problem of compile time program behavior analysis can easily fall into the realm of undecidability. Fortunately, it turns out that although semantic type checking in general is not decidable, it is co-recursively enumerable, which means that if a type violation exists, it can be discovered in finite time. The downside to that, of course, is that if no type error exists, then any checking procedure might run forever. It is a clear limitation, but can be mitigated. I won't cover it in this talk, but I will be happy to discuss it afterwards. So with all that, our project proposes a co-recursively enumerable type checker based on the semantic typing notion, meaning just to reiterate, if semantic type error exists in a program, our tool will be able to prove it in finite time. The advantage here is clear. Semantic typing allows for a significant improvement in expressiveness. We have incorporated some rather complex type into the theory, but it's not really surprising since the whole appeal of semantic typing is higher expressiveness. But what is surprising is that by nature of our design, these complex types are expressed with relative ease in our theory, which we shall discuss in detail soon. So, yay. Okay, I will now offer a rough roadmap of the rest of this presentation. First, I'll start by defining a small untyped language, which will be the basis of subsequent discussions. And then I'll introduce two relations that will define how type checking works in our language. Next, I'll give an example of how more context types can be introduced to the language and talk about the actual implementation. We'll also briefly discuss the practicality and the performance evaluation of the implementation. And finally, I'll discuss some limitations of our work and what we hope to work on in the future. So, our core language is quite a standard functional language with integers, booleans, and function values. There are a few minor quirks about this language that's necessary for type checking. First, it allows for some basic type casing via pattern matching using the tilde symbol. It also has these pig primitives for integers and booleans, which are essentially non-deterministic pigs during evaluation. Apart from the above-mentioned features, the language has standard syntax and small-step operational semantics. One thing to note about this, about the language is that although the language itself is untyped, we can verify whether an expression belongs to a certain type, i.e. whether the behavior matches the description of that type. Okay, now I'll give the model relation that defines what it means for an expression to have a type tau in our language. So here is the model definition. This is very similar to the standard inductive definition for basic types in logical relations. Intuitively, the cases for base types, int and bool in this case, state that an expression has type int or bool if it evaluates to an integer or a Boolean. And to type check a function, we actually need a full enumeration of the input space. For each value in the domain type, after applying the function to it, the application result must be a value in the codomain type. It's worth noting that for each clause, we're requiring all evaluations of the expressions to be a member of the specified type, which is to account for the baked-in non-determinism in our language. Another thing that may come off as a bit strange is that for function types, the definition doesn't really specify how the function should behave on arguments not in the domain type. That just showcases kind of a different philosophy of semantic typing. It only defines what's expected rather than what to exclude. But this particular model isn't readily implementable. For higher order function types, we cannot write an implementation that enumerates all possible function inputs. And as such, we need a more practical definition that can actually be implemented. So here's the second definition, TC, and TC defines how type checking actually works in our language. An expression has type tau if and only if the call to a checker function doesn't evaluate to error, and if it does evaluate to a value, the value has to be true. So what is this checker function? Below is the inductive definition for checker. The clauses for checking integers and booleans are quite intuitive. Again, it's simply type casing. The clause for functions is more interesting. We will formally define generator in a bit, but for now, you can think of it as a magical black box that will produce an arbitrary value from the given type. So with that in mind, you can see that it's doing something very similar to the more mathematical definition. To check a function type, you would generate an argument in the input type and then check whether the application result has the output type. So let's define generator. The generator's full definition is given below. Intuitively, the generators, when called, should give us an arbitrary value from the specified type. For integers and booleans, they're pretty intuitive. It's just their corresponding non-deterministic pick. The interesting clause is, again, for function types, there are two things that's happening in the generated function here. First, it will check whether the input is indeed in the specified input type. Then, after the check passes, you will produce an arbitrary value in the output type. So to sum up, here are some key observations about generator. First, it's responsible for introducing non-determinism to the checker whenever necessary. That is in the function type clause. And here's the definition for checker, just as a reminder. And also, according to this definition, generated function values will always produce outputs that are completely independent of their inputs. And that's bizarre, to say the least. So what that suggests is that our function generators, instead of trying to produce functions that have equivalent semantics to the real function in the type, they only aim to capture the behavior of these functions. That means for each run of a program containing a concrete function, if we replace that function with a generated function, there will be a set of specific choices for each non-deterministic pick that will result in the exact same program behavior. And that is the key to enumerating function inputs in the actual implementation. Overall, the key takeaway from this definition is the following. First, given a fixed type, both the checker and generator are just expressions in the core language. Second, checker is responsible for verifying the type of a value and will return false or error if the checking fails. And finally, generator is responsible for simulating the for all enumeration of a type. But before moving forward, you might be wondering, does that definition even make sense? Or more concretely, we want to prove that the more practical non-determinism-based checker is in fact equivalent to the model we first defined with respect to type checking, which can be summarized as the theorem shown on the slide. The proof can be found in our paper. The important takeaway is, with this theorem, we can safely use TC to realize semantic type checking in our implementation. But even with correctness proven, there's still the glaring question of what for if all this checker can handle is just simple types, then why not just use a type system? Well, as you might have observed by now, types are represented by a pair of functions in our language, a checker that verifies membership, and a generator that produces members in that type. This simple construction is actually very effective. we can express some really complex type with it. As an example, I'll demonstrate how we can extend our language with dependent function types. The syntax here is pretty standard. The model definition is provided as well, which again is pretty standard. It is similar to the normal function definition, with the only difference being that we need to substitute the argument into the output type when checking the application result. We also need to update the definition for TC to include dependent function types. The updated checker and generator for dependent function types are defined as such. As you can see, the checker mirrors the model definition really well. It generates a value from the input type and invokes the output type checker on the application after appropriate substitution. As for the generator, it's pretty much identical to how function types worked originally. The only difference, again, being the additional substitution. And that's it. Voila. Dependent function types added. OK, so after all this talk about theory, let's talk about some actual concrete implementation. Our language and type checker are both implemented in OCaml. We allow selective type annotation in the implementation, which means the user gets to decide what expression to check and what not to. As will be demonstrated later, type checking is encoded as an error reachability problem in our implementation. Backend-wise, we use a concolic evaluator to look for reachable error states. Also, the actual implementation includes many more types than the core and the one extension we just presented. The full list of additional features are laid out on the slide. As you can see, we've managed to capture some pretty complex type using our theory. Proving completeness and soundness for all of these features and their synergies are part of our future work. OK, now I'll go over how type checking actually works in our implementation in a bit more detail by walking through a simple example program. The example here is a constant function that returns 2. The return type here is clearly wrong. 2 is not a Boolean. And to type check this program, our first step is to transform the program to include concrete checks for the declared type. There is only one declared type here, but the same procedure can be extrapolated to programs with multiple declarations. The transformed version of the program is shown on the left. It's a little bit difficult to parse, so let's break it down. The highlighted boxes correspond to the key parts of type checking in the previous TC definition. Recall that to check function types, we need to generate an argument from the input type and then make sure the output is in the right type. In this case, we're generating a Boolean value argument and use type casing to verify if the application result is also a Boolean. Since 2 is the return value, it will not pass the type casing, returning an error. And now comes the second step of type checking in the implementation, using concolic execution to find any reachable error state. In this case, the goal of our concolic evaluator is this particular error clause, which signifies the presence of a type error. An example output is shown here. As you can see, our checker managed to spot the error in the declaration, correctly stating that the return type is an integer, which is different from the actual declaration. OK, here is a more complex example where we are implementing an insert function for AVL trees. The AVL tree type is highlighted in the yellow box, and it's a rather complicated refinement type on a recursively defined tree type. The error is over here in the red box. It's an incorrect rebalancing. So to detect this error, our tool essentially needs to be able to produce inputs that will lead to an AVL tree violating the declared type. Unfortunately, it is up to the task. It correctly identifies that the program implementation does not conform to the actual declared type. Speed and performance-wise, we compared our implementation with self-contra verification, more specifically with the artifact in 2015 paper, Relatively Complete Counterexamples for Higher Order Programs, which focuses on finding counterexamples to racket contracts, which is actually very close to us in spirit. We ported most of their programs from their racket benchmark into our language, and the result is actually quite promising. Our tool outperforms their artifact in most cases. The blue is us, and the red is SCV. Note that this is a little different from the data presented in our paper because we have included some optimization post-submission. And as you can see, apart from a few cases, our tool outperforms theirs rather consistently. In the number of cases that our tool does trail behind a little bit, the gap is small enough that we believe they can be addressed by further optimization. Finally, let's talk about some limitations and directions of future work. An issue we're facing is correct types. By virtue of being co-RE, our checker will time out on correctly typed expressions involving recursion. This suggests that our checker will probably work better as an add-on to a traditional type system, which is able to handle most of the simpler type checking. We also would like to extend our theory to include more complex effects, such as states and exceptions. Finally, we want to further optimize our backend implementation. There are many optimizations yet to be applied to the concurrently validator, and we believe our tool's performance will be further improved with these optimizations implemented. And that concludes my presentation. I'm ready to take any questions. Thank you.
We have time for a few questions. Can you step up to the microphone?
Do you think you'll give better error messages for these complex types using your add-on type checker?
Thank you. Yeah, error reporting is always a difficult problem, and we actually spend a substantial amount of time on trying to make the error message more intelligible. But yes, it is definitely a work in progress. Thank you for pointing it out.
So since we're at OOPSLA, maybe you can say a bit more about is subtyping presenting any significant special challenges for your approach?
Actually, yes, because record subtyping presents a sort of asymmetry in the generator and the checker pair, because when we're checking for record subtyping, we allow much more inputs than, say, when we're generating something, because if we say a record of type A with field A and type int, when we check it, if we see something that's more specific with a B int, then we can say, well, you also pass because we only look for A. But that's a problem for generator because generator now have to be able to come up with everything with A field of type int, but also everything else in the universe that happen to contain an A label. So that is a really big challenge for us. And we had to kind of work in a lot of restrictions in the theory in order to accommodate that. More details to be found in the paper. Please go read the paper. But basically, what we were doing to make that work in our system is to kind of put guardrails into our system to say if you kind of downcast your records to contain less information than it contains, you are kind of fixed in this state. After you are passed into a function that only takes in A int record, when you get out of it, you kind of just forget that you have a B field or a C field or whatever field you had before. That is just some sort of how we manage. I think it's kind of similar to how Java deals with it. Please correct me if I'm wrong, because I think we have some Java experts. My co-authors are in the audience. But that is not the ideal solution. We're trying to find a better solution to the problem. But yeah, subtyping is definitely a challenge.
Thanks very much.